Hello all, I'm Syed Nouman Hasany, and I'll be presenting our project Seg-XRes-CAM explaining spatially local regions in image segmentation. The other two members involved in the project are Petitjean and Fabrice Mériaudeau. Attribution-based post hoc methods have been quite popular in explainable AI. However, most such methods have been presented in the context of image classification. Some methods have been extended to other tasks like image segmentation. One such method is Seg-Grad-CAM, an extension of Grad-CAM to image segmentation. In the present work, we show that by virtue of its formulation, Seg-Grad-CAM does not perform well when it comes to generating attribution maps for a target class in a region of interest as compared to the entire segmentation map. Taking inspiration from high-res-CAM, we propose Seg-XRes-CAM, which takes spatial information into account when generating region-specific attribution maps. In image classification, attribution-based methods can primarily be divided into gradient-based versus perturbation-based. The method on the left is a gradient-based technique which simply visualizes the derivative of the output with respect to the input image. The method on the right is a perturbation-based technique which generates an attribution map by masking the image multiple times and then taking a linear combination of those masks. In image segmentation, grid saliency is one of the earliest works about generating attribution maps, and it utilizes a perturbation-based technique to try and learn the necessary context for a segmentation. On the right is U-noise, which tries to learn a model which can directly predict an attribution map given an input image. Now, a conventional computer vision model for classification is a convolutional architecture incorporating convolutional layers followed by a couple of fully connected layers. For example, if the following image is presented to the model, it assigns the highest score to the waterfall level. Now, if we want to generate an attribution map for this image, Grad-CAM provides us with a simple mechanism to do that. We first pick a layer to analyze, generally the layer just before the fully connected layers is chosen. Grad-CAM generates an attribution map by taking a linear combination of the activation maps of the selected layer. We now need to find the coefficients of the linear combination. In Grad-CAM, an individual coefficient is obtained by taking the global average pooling over the gradient matrix representing the derivative of the target score with respect to the particular activation map associated with that coefficient. Once we have found all of the coefficients, we can generate our attribution map and overlay it on the original image to see. A conventional computer vision model for segmentation consists of an encoder, a decoder, and a bottleneck layer between the two. Now, for example, for the following input image, the image segmentation model returns a segmentation map highlighting all of the cars. If we now want to generate an attribution map for this image, we can use Seg-Grad-CAM, which is an extension of Grad-CAM for segmentation. Once again, we first need to pick a layer, and it is common to pick the bottleneck layer. Similar to Grad-CAM, Seg-Grad-CAM generates an attribution map by taking a linear combination of the activation maps of the selected layer. Now we need to find the coefficients of the linear combination. In Seg-Grad-CAM, we first select a set of pixels which belong to the target class, and this is our region of interest represented here as M. Now we sum up the scores in this region, and any individual coefficient is obtained by taking the global average pooling over the gradient matrix representing the derivative of the sum with respect to the particular activation map associated with that coefficient. Once again, once we find all of the coefficients, we can generate our attribution map and overlay it on the original image to see. Now, what if we don't want the attribution map explaining all of the cars and we only want the attribution map for the leftmost car? We can once again calculate our linear coefficients, but this time our region of interest is only the leftmost car. However, our final attribution map seems to be highlighting all of the cars as being relevant to our prediction of the leftmost car, while we might at least have expected the leftmost car to be the most highlighted. If we repeat this for the third car from the left, we once again find that Seg-Grad-CAM highlights all of the cars as being relevant and does not extraordinarily highlight the car under consideration. In fact, if we observe the attribution maps generated by Seg-Grad-CAM for all of the cars versus individual cars, the maps are almost identical. So what is happening here? If we consider the case of all cars versus the leftmost car, the formulation of our final attribution maps is going to be as follows. In both cases, a linear combination of the activation maps. Now, the activation maps in both cases are the same. The only thing different in the two cases are the linear coefficients which carry the information provided by the derivative of the sum of scores. However, Because each activation map is assigned a single scalar coefficient, the spatial distribution of the activation map plays no part in the eventual linear combination, as all spatial locations in the activation map are scaled uniformly by the linear coefficient. This is why even when we only want to generate attribution maps for the leftmost car, there is no way for the linear coefficients to particularly highlight only the region surrounding the leftmost car, and hence they end up highlighting all of the cars. A potential fix for this is to instead utilize another method proposed in the context of generating attribution maps for classification, that is high-res-CAM. In high-res-CAM, instead of taking the global average pooling, the gradient matrix is element-wise multiplied with the feature maps, hence ensuring that the signal present in the derivative impacts different spatial locations accordingly. If we look at the maps generated by utilizing high-res-CAM instead of Grad-CAM, we can see that high-res-CAM only highlights the leftmost car as salient, as opposed to Grad-CAM, which highlights all of the cars. Further corroboration of this attribution map is achieved when we utilize RISE, which is a model-agnostic perturbation-based method in order to generate the attribution map, and it also only highlights a region focused on the leftmost car. We can further generalize the formulation of high-res-CAM in order to control how fine or coarse we want our gradient signal to be. We can do this by first applying pooling, followed by upsampling before the element-wise multiplication happens. In this way, by controlling the pooling window size, we will arrive at the results of high-res-CAM on one end of the spectrum and arrive at the results of Grad-CAM on the other end. One way in which these attribution maps can be analyzed or evaluated is by utilizing them to mask the image, followed by getting the model's prediction on the masked image. We can compare the model's prediction on the masked image versus its prediction on the original image in the region of interest, and we can do this using DICE. Additionally, we can also note the percentage of the image preserved by our attribution map. As we can see, Seg-XRes-CAM retains a smaller portion of the image and still gives a better DICE than Seg-Grad-CAM. To conclude, we have shown that by virtue of its formulation, Seg-Grad-CAM does not take spatial information into account when it comes to explaining a target class in a region of interest. A potential remedy is to utilize Seg-XRes-CAM, which is a generalization of Seg-Grad-CAM and Seg-High-Res-CAM, and it takes spatial information into account when generating its attribution map. Some questions for future exploration include the choice of layer, because here we only focused on the bottleneck, as was done by Seg-Grad-CAM, and also an extensive quantitative comparison between Seg-XRes-CAM with some of the perturbation-based methods like RISE. Thank you.